metric along the leaves, which would be of constant curvature. So it would be a smooth metric along the leaves and maybe continuous in the transverse direction. So these two questions, I think are rather natural. And as I told you, the answer to these two questions will be no. Okay. Well, it depends. You will see. Okay. So let me, before I start describing very nasty examples, or very nasty for laminations, giving counterexamples, let me begin by the very elementary and very classical and easy case, the elliptic case. It's very easy. So let us assume that we have lamination, and let us look first at the spherical leaves. That is, those leaves which, as Riemann surfaces, are CP1 spheres. Then we have the very classical and old Reb stability theorem, which says that, well, really there is no problem. It says that the set of elliptic leaves of any lamination is open. If you give me a lamination, if you fix a spherical leaf, then the nearby leaves are also spheres. And moreover, in this neighborhood, the lamination is just given by, is just a fibration, a nice locally trivial fibration over some base. So really, on that open set of spherical leaves, everything is nice. So one good idea is to throw out this open set so that what's left is a closed set. And we have a closed sublamination in which we have no more spherical leaves, and we are going to forget about spherical leaves. So we forget this, and from now on I will assume that all my laminations have no spherical leaves, because otherwise it will be just easy. Well, not so easy actually, because if you think of question number 2, then you have this nice theorem. If you have a continuous family if you want to solve question 2 in the case of spherical leaves, you need a continuous version of uniformization theorem. So you need Alphonse Berce or something like that. So it's not completely trivial.
No
so, what?
No minimality property.
No minimality property. Well, let me tell you something, the truth. This is a theorem that I've never seen the proof. Reb stability, Reb proved it in 56 or something like that. Of course, at that time, he was looking at foliations. And he got stuck, but he could prove it only for C1 foliations, because he needed some kind of transversal vector field, some kind of C1 transversal vector field. Well, it seems to me, and it seems to everybody, that this has nothing to do with the problem. Really, Reb stability theorem is an abstract theorem on lamination like that.
Topology.
Topology, yes, but nobody did it. I've never seen a proof of this Reb stability theorem in the context of abstract. You need flow boxes, you need some kind of transversals which are compatible. It's not completely obvious, but I believe it. Otherwise, I wouldn't tell you. Well, that might be.
Not interesting.
No comment. Okay, so before I try to go into these rather difficult questions of trying to uniformize these laminations, I need to come back to our problem. We recall that we have the problem that many laminations have no foliation cycles. They have no fundamental class. So the idea is that we want to do something else that will be a weak version of it. And this notion is the notion of harmonic current, which has been already discussed by Vadim Kajmanovic in his talk. So let me recall that in this context rather quickly. The point is that, as I told you yesterday, on a given lamination X, you can discuss differential forms. So differential forms are only defined along the foliations and are smooth along the foliations and continuous in the transversal direction. So for example, omega 0x is only, means only the space of functions, and omega 2 of x means the space of two forms. And a nice fact, using complex analysis in the classical way, is that we have a nice operator, which is the Laplace operator, which is square root of minus 1 dd bar. Square root of minus 1 is only there to make it a real operator. I think this is the same operator, maybe 2 pi ddc. This is the Laplace operator going from functions to forms. And the definition is this. The harmonic current is exactly like yesterday for foliation cycle. We want to be able to integrate forms. So harmonic current is a linear map on two forms, which is positive and positive forms, just like yesterday, and we will weaken the definition of foliation cycle, and we ask for that. We want the integral of a Laplacian to be 0. Since there are less Laplacians than exact forms, this is weaker than the definition of yesterday. So if we have a foliation cycle in the definition of yesterday, then this foliation cycle as a linear operator is also the harmonic current. Okay. And the theorem is that, due to Garnet, is that any lamination on any compact space has at least a harmonic current. And the proof is very simple, just in the same spirit as yesterday for the hambana theorem. Picture is this. The picture is this. I draw the picture of the vector space of two forms, and in this vector space of two forms, I have two things. One is a positive cone, the cone of positive two forms, and a subspace, which is the subspace of Laplacians of functions. So this is the vector space of all functions of the form square root of minus 1 dd bar of some function. So I have two objects like that, a cone and a space, and these two things can have two possible configurations. Either, like on the left, the space does not intersect the cone unless on the origin or on the vertex, or the space intersects non-trivially the cone. This second case is not possible because that would mean that there is some function f whose Laplacian along the leaf is positive. Now, if you look, since the space is compact, this function has to achieve its maximum somewhere. And at that point, we get a contradiction with the maximum principle. Okay? A function cannot have a local maximum and have this, at the same time have a positive Laplacian. So it is impossible to have a positive form which is a Laplacian of a function. And in the second case, that means that we have a cone which is disjoint from the space. So by hambana, there's a linear function which is positive on the cone and 0 on the space. But this is what the definition of harmonic current means. So in all cases, we have a harmonic current. So this is something which is quite nice because it's not as good as a fundamental class, but it's useful. One of the things that we can do with this harmonic currents is that we can integrate forms, and in particular we can integrate curvatures. Let me explain a nice formula. This is a formula I like. Well, this is one of the few formulas that I like. You know, it's the following thing. You take a Hermitian metric on some Riemann surface, G, and you consider its curvature. Curvature, you can think of it as a function, or in a better way, I think it's better to think of it as being a two-form. The curvature of a metric is a two-form. So I denote by G the metric and by K the two-form, which is the curvature. And the formula I like is the formula that tells you how the curvature changes when you change the metric conformally. So the formula is this: you change the metric g and you multiply it by a positive function. So a positive function can be written as exponential of somebody. I write it as exponential of 2u because after all a metric is a quadratic form, so what we are really interested in is length, which is square root of the metric. So I change the metric and I define a new metric g prime to be exponential of 2u times g. So the still metric is converted to the first one. And the formula says that, well, curvature changes just by the Laplacian of u. So the new curvature k prime is equal to the old curvature k minus 2 square root of minus 1 dz bar u. I hope I didn't make a mistake on the coefficient 2, but this is not important. So really, when you change metric conformally, the curvatures change by some Laplacian. But by definition of a harmonic currents vanish on Laplacian. This is definition. So, in particular, we get the theorem due to Gauss and Bonnet that the integral of the curvature does not depend on the choice of the metric.
Only on the conformal class.
Yeah.
It has a Riemann surface. Yeah.
On the Riemann surface. The integral, the evaluation of a harmonic current on the curvature makes sense and is independent on the metric. So this is a nice feature because this tells you that if you have a lamination, if you give me a harmonic current, then associated to this harmonic current, you have a number. This number, you would like to call it the Euler characteristics of the lamination with respect to the current. That's natural definition.
So there's one normalization, right? The total mass is 1, right?
That's a central point. There is no natural. This is a bad point of the theory. There is no normalization. How would you say the total mass of the current? You know, this is one. I think this is one of the tricky points. For a harmonic current, just like a transverse invariant measure. Take a transverse invariant measure. There is no way of normalizing by saying, well, I want total mass 1. Right. Doesn't make sense. Right. Everything is projective, but there is no canonical basis. So I wish I could find some clever way of saying, well, I think it's not possible to normalize the total mass of a harmonic current by something. One way of doing it would be to select a Hermitian metric along the leaves, but this is not natural.
So what is the integral? I carry is the curvature you think of it as 2 forms.
Yeah, this is the point of today.
Oh, so
curvatures are forms.
Huh?
Today.
Okay.
Well, another day will be maybe number, but today it's a form. Okay, so what can we do with these numbers, with these Euler characteristics? Well, we can try to evaluate them. And let me mention a theorem which is the following. So originally it is due to École. He proved it when the measure is when the harmonic current is indeed a Foliation cycle. And the spatial cadence is a Foliation cycle, and I generalized it later in the case of any harmonic current. So it tells you the following. If you pick any lamination, and if you assume there is no spherical leaf, we said this is no assumption at all. So you assume there is no spherical leaf, and then we pick any harmonic current. We know that there are always such currents, I. And then when you evaluate these Euler characteristics I of k, the theorem says this is always non-positive. And the second part of the theorem tells you exactly when this is 0. It tells you that this is 0 if and only if I is not any harmonic current, when it is a foliation cycle, and moreover, when almost every leaf with respect to that foliation cycle is of parabolic type. So this is a kind of a way of splitting laminations into something that we would like to call parabolic and something we would like to call hyperbolic, depending on the sign of this image. So I must say that, in order to prove this theorem, in order to prove this theorem in the general case of harmonic currents, I use the theorem of Cohen, which is the exact same statement, but replacing here harmonic current by foliation cycle. But I am unable to prove directly Cohen's theorem. And I'm very unhappy with that because I don't understand his proof.
20 years ago, you asked me whether Kahn's theory had any application to foliation.
That's a good
I gave
example.
this example.
Yeah.
So,
Yeah. It's still a good example. Okay, so
might be other examples.
before I go to a description of bad examples of bad laminations, let me give the good point, the good news. Good news is that everything is okay and everything is nice, at least in the hyperbolic case. Oops. So, here are the good news. This is the theorem of Campbell. It tells you the following. If you have a Riemann surface lamination, and if you want to know if it's possible to find a metric, a Hermitian metric along the leaves, which is continuous in the set, and which is smooth along the leaves and has constant negative curvature along the leaves, then this happens if and only if, for every foliation cycle I, the Euler characteristics I of k is negative. Of course, it is clear that 1 implies 2, because the integral of a negative number is negative. So the main problem is to prove 2 implies 1. You start with the assumption that for every foliation cycle, the integral of k, the Euler characteristic, is negative, and you prove that there is a hyperbolic metric along the leaves. This nice theorem, and I've written here 2 examples in which it applies. The first example is, well, if there is no foliation cycle at all, then the condition 2 is vacuous. So property 1 is satisfied.
Vacuous and true.
Vacuous and hence true.
Right.
Yeah, yeah. So if there is no foliation cycle at all, then there's a metric which is hyperbolic along the leaves. And this special case of Cambell's theorem was proven by Alberto Verhofsky in the case of hyperbolic leaves. Or another case would be, well, assume there may be some foliation cycles, but assume every leaf is hyperbolic, abstractly. Then it follows from the theorem on the other slide, it follows from this theorem that the I of k is negative. So really, if every leaf is hyperbolic, then we have a nice hyperbolic continuous metric on the set. So the summary of this is that in the hyperbolic case, everything is really fine. We have a good metric which is hyperbolic curvature -1 along the set. So now let me go into the...
So that means the theory can start now. Right?
Yeah,
Start.
exactly.
It can
Exactly.
start, yeah.
Exactly.
At the Riemann point. Yeah.
Yeah. Now, let's have a look at the parabolic case. So basically, I want to construct today for you 2 counterexamples. First, I will describe an example of a minimal lamination. So all these are X, in which there is an actual mixture of parabolic leaves and hyperbolic leaves. So we don't quite know on which side we would like to put them. And the second counterexample I want to show you is an example where all leaves are parabolic. So there is no mixture, but it is not possible to find any flat metric along the leaves. So this is the program for the So let me begin by the first one. So this first example I'm going to describe, well, it's due to Rick Kenyon. He explained it to me, we discussed that, and we simplified it, and this is his example. So I'm going to construct an example of a Riemann surface lamination on a compact space with the following properties. 1, all leaves are dense. 2, all leaves are parabolic except exactly 1, which is hyperbolic. And 2 more properties are written there, but this is not very important. There is no holonomy, and each leaf has polynomial growth. But if you don't know what this means, this is not the basic point. Really, what is basic in this example is that I'm going to construct something in which almost everything is parabolic. Right in the middle, one leaf is different from the others. Okay, the construction, I think it's rather nice. Let me show you. Well, it's kind of a construction like yesterday on the space of tessellations and things like that, but it's kind of variation of the same idea. First, you begin by constructing some kind of compact metric space, which is the space of all trees which lie in plane and whose vertices are on the integral lattice. And the lattice integral on R2. And with a base point at the origin. So I'm looking at the set of trees containing the origin and having the property that everything is drawn on this lattice. So I've drawn the lattice in black, and the green part is one element of that set. Now you make a topology out of that, just like yesterday. We say that... No, infinite tree, probably. Sorry, my pen is finite pen. But this is... Well, there might be finite trees, but I'm going to roll them out in a moment. But this is a very big thing. Okay? So I make a compact space on that, just in the same way as yesterday. Well, you take 2 trees, and you want to know if they are closed in this topology. So what you do is that you take a big ball in the plane, and you look at the restrictions of the 2 trees on that big ball. And here there's a little subtle point. You consider the connected components of these intersections containing the origin. And you say that the 2 trees are closed if this connected component is the same for the 2 trees in a very big ball. Okay? So 2 trees are closed if they agree during a long time, and maybe after a long time they begin to diverge. Okay? So by a kind of usual diagonal process, this is compact space, compact metrizable space. And this space is also nice because it's kind of foliated space, because if you have such a tree, you can move around the base point by integral translations. And you get another tree with another base point. So really, on that space, you have a dynamical system, just changing the base point on the same tree. The orbit of one point is just one tree with all its points as base points. So that's nice contrast. Now, a very simple way, very simple, I hope you understand it, it's very obvious. There is an obvious way to transform this object into Riemann surface lamination. You make it thick. So here's the picture. From that space, I'm constructing a lamination. So just by a very elementary thickening process. That is, the tree is some kind of one-dimensional object with branching, and you just replace each elementary part of the tree by tubes. If you see in your tree somewhere some vertical edge like that, you replace it by a small cylinder. If you see some kind of a cross like that, you replace it by a cross, by some, how do you call that? You know, another cross.
String theory.
String theory. Okay, so, this is string theory?
Yeah.
Sure. Oh, I'm very pleased to learn. I'm a string theorist. Wow. You know, my kids will be very proud of me. Okay. Okay, so then you glue all of these things, and so that you construct a compact space, let's say T tilde, which is just essentially the same one as before, except that it's now thick. And it is equipped with a lamination by Riemann surfaces. So to give you an example, if somewhere in the tree you see such a picture, then the leaf which is corresponding to that picture will be the boundary of some kind of trivial neighborhood of this tree. You see this complicated Riemann surface? So really, you get a very complicated Riemann surface lamination in a compact metric space. Okay, so this lamination is not good for us.
Yeah, they're all hyperbolic.
Because this lamination is too big. It contains many spherical leaves, for example. Well, finite tree. Among the trees, we have finite trees. And if you take a finite tree and if you do this construction, what you're going to do, you get a very complicated sphere. But a sphere. So among the elements of my sets, of my foliation, lamination, there are spherical leaves. And there are also many hyperbolic laminations, because there are many complicated trees with many ends. Yeah?
The spherical leaves are isolated.
The spherical leaves are isolated. This is an example of application of Rev stability. That's an example of Rev stability in this context. Okay, so this lamination is very complicated, very big. It has many non-desirable objects. What you want to do is to take some sub-lamination of that lamination. And the lamination I'm going to discuss will be the closure of a very well-chosen leaf. So now let me explain how one chooses one very specific tree, and the counterexample will be, well, the closure of that leaf. So here's the construction. It's kind of a, I don't know how I should call that, something like penhole styling or self-similarity. Let me show you. Well, the tree that I'm going to pick in that space will be constructed by induction. Here's the process. You start with this cross. It is twice as long as wide. Then you take four copies of it. You take one copy of it, this one. Then take a rotation by 90 degrees of it. Then a rotation by 90 degrees. Then rotation by 90 degrees. And do it again. This part here is the same one as this one. And rotate, and do it again. And again, and again, and again. Okay? Is the construction clear? So this is a very inductive construction, and you do it again and again. And at the end, not the end, before the end, you get this picture. Here's the picture that you get. It took me a long time to do it. I have no computer. Oops. So you get this picture. You know, this is an interesting picture because it's a tree. You know, it's a
maximal tree.
It's maximal tree. So let me tell you what are the points in the plane which are not vertices of that tree. Okay? So a point in the plane has two coordinates.
There's a loop up there.
There's a loop?
Yeah. Up there. 10 o'clock.
Where is it?
10 o'clock, halfway towards 11 o'clock, yeah.
So, Ah, yeah. No, okay. There shouldn't be loop. This is like a chemical defect.
No, but it's just an extra line you put.
Yeah,
Just
right.
an extra line.
I don't find it anymore.
Just above the smudge.
Forget it. Okay. Okay, so just let me give you, this is a simple, interesting exercise from elementary number theory. You pick a point in the plane, has two coordinates, A and B, x and y. X and y are integers. Throw out those points for which the two-adic valuation of x and y are the same.
What?
The two-adic valuation. Throw out these points for which the two-adic valuations.
Same power of 2.
Yeah, they contain the same power of 2. So you throw them out. Exercise, you get a tree. What's left is a tree, and this is this picture. Okay.
Is there something special about 2?
No idea. No, I don't think so. No, because this embeds in the two-adic. No, I don't think so. So what's about this picture? This picture is a tree, I told you. And what's the topology of that tree? You know, we have a middle point here. And from that point, we have 4 infinite half lines going out of it. And the claim is that this tree has only 4 ends. Because it consists basically in 4 infinite lines on which we glue finite objects. We have here a finite object, a bigger one but finite, and a smaller one, and then a bigger one. But in any case, what really we have is a cross with 4 ends, and from time to time we put some finite object. So,
So
the topology of the corresponding leaf is just something like that. We have an infinite horse, and then we have some bubbles. But from the topological point of view, this is just a sphere minus 4 points. So this sphere, this leaf, is a sphere minus 4 points. Now what's happening when we consider the closure of that leaf in the space of trees? Well, we have to move the base point. We move it around and take limits. But when we move this base point around, this cross, this middle point, the central point, typically we go to infinity. So it will disappear from our screen. It will become something like that, for which there is no more 4 ends. The typical orbit now, after moving the point, the base point around, and putting it to infinity, a typical leaf will be basically an infinite cylinder with bubbles. Some very complicated thing like that, but a cylinder. And it is quite easy to see that this cylinder is a parabolic cylinder, just by counting moduli. So really, almost every leaf is parabolic. And one leaf is hyperbolic. So the unique leaf, which, well, there are some things to check and prove and things like that. The only leaf which has more than 2 ends is this leaf going through that point. All others are parabolic, and what is a little bit more difficult is that these leaves are dense in their closures. This is due to the fact that this situation is quasi-periodic, because the construction has been done in such a way that this is self-ciliar. So really, the closure of points, the closure of orbits are dense in themselves, and this is classical physics. This is not difficult. So really, we get a nice example. This is lamination. The growth is polynomial. There is no polynomial. All leaves are parabolic except one. Okay? That's okay?
What's the transversal structure?
This is Cantor set.
This is not a fiber bundle.
What?
It's not a fiber bundle.
A fiber bundle.
Okay, trivial.
Well, I think it's a fiber bundle over some, probably over some compact linear surface, but with Cantor set as fiber. I think so.
You know, there is a sense in which it's homogeneous, because Brownian motion is still recurrent.
That's a good point.
It's still, so it's like a topologist prejudice here.
Yeah, I want to make a comment in a moment. I'll do this comment in a moment. Yeah. So the exercise today is show that this does not embed in CPN. That's quite the proof. Let me give you a hint. The hint of the proof is what Ilyashenko explained to us. Holomorphic curves in Keller manifolds are minimal surfaces. So you cannot have any kind of vanishing cycle for a sub-lamination of complex holomorphic projective space. And this object does contain some kind of vanishing cycle. Think about it, and that's a proof. Actually, yesterday when I was writing this transparency, I did this exercise and I said, well, I don't know if the following is true. Maybe if we take a lamination which by assumption sits inside projective space, maybe this kind of phenomenon is not possible. So, question, is it true that a lamination embedded into projective space
Pure.
Minimal, what?
It's pure.
Yeah. is pure in the sense that there is no mixture of hyperbolic and parabolic.
Not with minimal.
With minimal. Did I say it? Yeah, with minimal. Well, when I explained this example to Marco Bonella, he told me, well, your examples is nothing. It's not interesting at all. And he was making the same comment that Dennis just made, that the sphere minus 4 point, from the potential theory point of view, is just a sphere. The Brownian motion does not see the 4 points which are missing. So a sphere minus 4 points, yeah, you would like to call that parabolic. And actually people from Riemann surface theory call that parabolic. So that's another question. Is it possible to mix parabolic and hyperbolic with this new definition? Good question.
You could say recurrent and transient.
Yeah.
Then you wouldn't have to change the
Yeah. Okay, so that was, but in any case, this lamination has definitely no flat metric around leaves. Okay, so that was first example showing that it is possible to mix parabolic and hyperbolic in the same minimal set. Second example I want to show you is I want to show you an example of lamination on a compact space with the following property. 1, all leaves are dense, it's minimal lamination. 2, all leaves are parabolic, so no phenomenon like I just explained to you. And 3, it is not possible to uniformize it, in the sense that it is not possible to find any flat metric along the leaves, not even continuous, but not even measurable. So I want to find an example of such an object which is not, has no flat metric, measurable flat metric along the leaves. Construction goes like that. This are one of my favorite objects. Well, I think I'm not the only one in the audience to like SL2C and subgroups of SL2C. So you start with a subgroup of SL2C, gamma, discrete, and you assume the quotient is compact. Then you get a nice complex three-dimensional manifold SL2C modulo gamma. We were discussing that yesterday. And you look at the C action of on M, which is given by the formula I just described, left translations by Unicode of matrices 1, 0, T1. This gives you a very nice holomorphic action of C on a compact complex manifold. Hence, you get the two-dimensional laminations on that three-dimensional complex manifold. Of course, this is definitely not a counterexample, because this lamination is given by a holomorphic vector field. So on the leaves, by definition, you have a time, t. So you can define a metric, which is dt modulus of dt squared. And this is, the leaves are flat by definition, because they are given by the orbits of a vector field. Locally, a piece of orbit is a piece of C, so you can put the flat metric. So this is a very nice flat metric on the compact manifold. So what we want to do is to take this object and modify it a little bit to kill the vector field and to keep the parabolicity of the manifold, of the foliation. So the construction goes like that. You modify the action of gamma on SL2C. So this is one of my favorite tricks. You choose some homomorphism, I denoted by omega, some homomorphism from gamma to C star. Well, it is a nice fact that some gammas have non-trivial homomorphism to C star. And then, so I denoted by omega goes to omega star, and then I change and modify the action of gamma on SL2C in the way that I described here. So an element gamma acts on an element G. Gamma lies in gamma, G lies in SL2C, and this is a thick point, meaning that I changed the action. And the new action is this. The action of gamma on G is obtained the following way. First, you multiply it on the right by gamma inverse. And then you multiply it on the left by the diagonal matrix omega gamma inverse. So this is a nice action of the group gamma by biholomorphisms on SL2C. And it turns out, it is now difficult to check, well, I should say first that if omega is trivial, meaning if I send everybody to the point 1, then this does not exist, so I just get the usual right action of gamma on SL2C, and the quotient is just my previous manifold SL2C modulo gamma. And the nice fact from topology, not very difficult to check, is that if you modify, if omega is close enough on a given system of generators, is close enough to the trivial homomorphism, then this new action of gamma on SL2C is still free, proper, totally discontinuous, and so on action. So you can go to the quotient. And you get a nice complex manifold, M sub omega, which is, say, infinity diffeomorphic to M, but definitely not biholomorphic to M. It changed the complex structure. So this is a nice complex manifold. And the good thing about this is that this new action does not commute with the C action by multiplications by unipotent matrices. You know, this new action of gamma on SL2C does not commute. However, this new action normalizes it. In other words, if you let gamma act in the new way I described, it is not commuting with the C action, but it is sending C orbits to C orbits. So the foliation generated by the C action is gamma invariant, which means that this foliation goes down to a one-dimensional complex foliation on this complex manifold M omega. But the fact, and this will be our example, let me explain. I'm not going to prove it because there are some subtle points to do, but let me explain what's happening here. What's happening is that
Well, if there were a metric, wouldn't that homomorphism have to be in the unit?
That's based that you have to measurable. So you have to, let me say something. Yeah, the basic point is another formula. So I'm writing two formulas in one talk. This is a matrix formula. So this formula tells you that uniform matrices do not commute with diagonal matrices. You know that.
The left-hand side is invertible, the right-hand side isn't.
I think I should not prepare transparency that night. I was only taking care of this coefficient because I knew the other three. Okay. Okay, so this formula tells you that the metric dt squared for the C star, the C action, is not invariant by the new action, but is multiplied by a constant. So really, on this new foliation, on this new manifold, there is no canonical metric. So the point is to prove that there is no metric. So to prove that there is no metric is not so easy if you want to prove that there is no flat metric which is measurable transversally. If you think a little bit about this question, what does that mean to have a metric like that and so on, you hit against the problem from ergodic theory, you hit against the ergodicity of the whole cyclic flow when you lift it to an abelian cover. But you have a theorem available to prove it. It's not difficult. I don't know. Once you make the connection with ergodic theory, then you take a theorem and then you get the proof.
I can give you another example of that.
Oh.
So you can take a rational map,
Yeah.
a critical effect map to make the lamination come back. So you can associate take a natural extension, the natural extension, with rational map. You have a lamination out of there.
Yeah.
There are fine lamination and a fine lamination with parabolic rays.
Yeah.
And typically,
It's all
it
the same.
does not have clear metric.
Is it really a lamination in my sense? Everything is okay?
Yeah,
There's no single point,
You can make
no bad points, and
well, you should be able to tap on the topology.
yeah,
Right topology there, then it will be a two lamination.
I see.
And typically, so when the substance order for this hyperbolic, it is not like lamination.
I thought your examples were not really the same kind of objects. They had some bad points.
No. But there are sometimes there are orbital points.
Yeah.
You can have the measure without
Okay.
orbital points.
Good news, but I prefer to see because this is, that was in my crib. Okay.
But I mean, I think the real point is that the theory of these laminations is organized by an affine profile.
Yeah, I wanted to say that. Yeah.
I mean,
So I wanted so these examples are bad because they show bad phenomenon and so on. However, there are still good news, even for parabolic laminations. So I wanted to mention two good news. One is this, that indeed, if you have a foliation by parabolic leaves, a leaf has no canonical flat metric. I explained to you, there's this problem of the scaling factor. This is what the problem that we have is the scaling factor. But there is an affine structure which is canonically defined. And good news number one is that if you have a lamination on a compact space, then the affine structure is continuous in the manifold. This is not difficult, but it's, I think, basic. If you have an affine lamination by...
Oh, that's the real theorem then.
That's the real theorem.
Another statement was the wrong statement.
Yeah. That's the answer to your very first question.
Correctly.
Yeah. The question is such that this theorem is yes.
Okay.
But I still like flat metrics. So this is why there is a second theorem that says that, well, yes, it's almost true.
Well, the scale is...
No. Let me explain that. Theorem 2, the purple theorem, says that if you have a lamination which is such that all leaves are parabolic, then it is possible to find a sequence of metrics for which the curvatures tend to 0. Okay, you could say, well, just take any metric, multiply it by 1,000, then the curvature is divided by 1,000 squared. This is true. So So it is going to 0. But this is true for all laminations, even non-parabolic. However, the curvature form is invariant to the scaling. If you multiply a metric by a constant, well, the curvature is divided by the square of that constant, but the area form is multiplied by the square of the same constant. So the product is constant. Well, this is Gauss-Bonnet. Okay, so really what has a meaning is the curvature form. And this is why this theorem has a meaning. It tells you that if you start with Riemann surface lamination with parabolic leaves, then it is always possible to find approximately flat metrics, meaning metrics with curvature forms. This is why I underlined the word form. The curvature form converges to 0 uniformly. So quickly, get the proof. Proof is as usual, hambana. Okay. Hambana. Well, recall this nice formula. Change the metric by conformal factor, then the metric changes by the Laplacian. And we are looking for a sequence of metrics whose curvatures tend to 0. So by this formula, we are just trying to show that we can write the curvature form K, which is given as a limit of Laplacians of functions. So the hambana theorem tells you that you can approximate a function, an element of a topological vector space by some subspace, even only if you cannot find a linear function of vanishing, blah, blah, blah. In other words, in order to show that this this form lies in the closure of that subspace, it is enough to show that any linear function of vanishing on that, vanishing on K. So the point is to show that I of K is 0 for every harmonic current, because by definition, harmonic currents vanish on these bar functions. But this is exactly what we have seen in the Cohen theorem, that if all leaves are parabolic, then we know that the Euler characteristics with respect to I is indeed 0. So we know that. So K is in this closure, so the metric can be approximated by a sequence of almost flat metrics. Okay, so I have here a slide. I'm not sure. I don't know if I should show it to you, because when I wrote this, I discovered, I've written that somewhere. It is published somewhere, and discovered yesterday that this is wrong. This is wrong because the harmonic currents are positive, are functionals which vanish on that space, but which are positive and positive forms. So there's something missing here. Do you agree that this proof is not convincing? I mean, you were convinced for a minute ago, I think.
Well, we were believing you, we're trying to understand.
Okay. Okay, so there is a small remark to make the proof correct. I should not show it to you. Okay, so time is over. A little bit more than 1 year ago, I was in this country and I went to a bookshop and I found a very nice book explaining how to give talks. And there was very many interesting hints. And one of the most important suggestions is this. The guy said, well, when you give a talk, you should first tell them what you are going to tell them. Then you should tell them. And then you should tell them what you just told them. So let me do it. So let me give a summary of today's talk. So today I explained to you that this Hale stability theorem says that in the elliptic case, no problem. We have seen that in the hyperbolic case, really, we have a nice theory. As Dennis was saying, you can begin the theory. You have a nice setup to begin the theory. And I try tomorrow to go a little bit further and to try to mimic our great-great-grandfathers like Riemann and Poincaré try to build automorphic functions of them. Well, in the case of parabolic cases, we have seen that it might be complicated, but there is still some hope because of this continuity of the affine structure. So maybe the point is that we should forget about flat metrics, except that we have some kind of weak version of it. We have almost flat metrics, which might be useful in some cases. And finally, and this is the point really I don't quite like, some cases you could have just a mixture of hyperbolic and parabolic leaves. And for the last bad news, the good news might be maybe you should replace the notion of hyperbolicity by the potential theory point of view and try to prove a positive statement which would be using the potential theory point of view instead of the topological point of view, geometrical point of view. Thank you.
Any questions?
What does harmonic current look like in a hyperbolic lamination?
That's what's your favorite hyperbolic lamination? Give me your lamination and I will give you the...
Solid.
If you take the solenoid, it's very easy. The harmonic current locally disintegrates as a positive harmonic function times a measure. In this case, this positive harmonic function is just the Poisson transform of direct mass to infinity. So you can see it.
That's unique?
In the case of expanding maps, it's unique. Yeah, in most cases, it's unique. This is not a statement, this is a feeling that the most interesting laminations have a unique harmonic current. For example, I could mention one case, collimator in three manifolds. I would suspect, with no compact leaf, I would suspect that it's always true that there's a unique harmonic current.
This is not exactly a question, but it's a comment. I mean, you could say, just a slight change of point of view, that you start from a geometric and topological setting, assuming compactness, and when you use it to build some measure theoretic thing, like a harmonic current, then you always have the ergodic decomposition. And for your later analytic calculations and for your currents and your homology, you can now pass to measure theory in the transverse direction. And then it is pure.
It's ergodic.
By definition, because you can't have a measurable partition. So,
well, the main,
you sort of change your point of view.
Yeah, the main point is to know if you want to understand topological objects or measurable objects.
Well, no, usually in some argument in geometry, you're going to pass to some quantitative step, maybe, so then you can do this.
About the theorem of flat approximation, what does it imply about the growth of the...
About the growth of leaf? This is a good question. I don't know if this implies polynomial growth. I would suspect it, but it does not imply immediately polynomial growth, but who knows? Well, maybe the theorem of David-Casanova, which implies something. It implies sub-exponential. Sub-exponential, yeah.
What's the statement?
Sub-exponential growth implies if the generic leaf is the complex C, then the growth is sub-exponential.
Oh, for the typical leaf.
For the typical leaf, yeah.
Thanks again.